Hi, everyone. So today we have Rosa Orellana, who'll be talking, or from Dartmouth College, who'll be talking about restricting Howe duality, a multi-set partition algebra.
Okay, so I want to talk about work that I have been doing with Mike, as you know. So I always get very nervous when I speak at York because I feel that Mike already told you everything. And until you're annoying. Anyways, so I want to tell you what like what we have been doing, even though all of you already know. Okay, so I want to begin with something hopefully that all of you know, right? So I want to talk about Essen Actions in this talk. And so here, right, we have an Essen action that a lot of you probably have learned already. And here I'm going to use Essen for the symmetric group and this boldface letter with a partition to indicate the irreducible representations of lambda. And I'm going to think of the partitions with just being Young diagrams, drawing upside down. Because that's how I feel the most comfortable when I'm doing it. Okay, so here you have so when you have a group action, right, the group actions that we are interested is when the group is acting on a vector space. And here we can make it very concrete, right, and choose a basis, and you could think of this as the standard basis if you like. Then we know that it has dimension n, right? Then for any positive integer, you can define the tensor product, right? And as a basis, this one is just, you could think of them as just these tensor products of k terms where the k's are chosen from here, right? Like, so all possible words that you can form, if you like, right? Where the letters are coming from this set, okay? So then SK will act on this tensor space, yeah, by permuting the factors. So here I give you a little example. So because I will have different actions on tensor space, notice that what it does, right, the permutation 1, 2 simply flips the two, like the places, right? So it's the permutation action. And then one thing when we are talking about representation theory, the main question is after you define an action, right? And that gives rise to a representation, right? You want to know how it decomposes in terms of irreducibles. And what that is asking is how many each of the irreducibles will occur when you decompose it. So that's the one of the main themes in representation theory. You have representations that you define, via actions. Once you have them, you want to decompose them. And in this case, we know that these coefficients turn out to be semi-standard Young tableau, or what Mike calls column strict tableau if in his talks, of shape lambda. And here the boxes are filled with numbers from 1 through n. Notice this n is this n right here, and the Young tableau will have k boxes because this is a representation of SK, right? So you have tableaus with k boxes that are filled with numbers 1 through n, and the semi-standard condition simply tells you that here is the little example that the numbers have to increase weakly in the rows and strictly in the columns, right? So for instance, here when n equals to 2 and k is equal to 3, like you have tableaus with 3 boxes. So these are the 3 possibilities, yeah? And then you're going to fill them with numbers 1 and 2, right? So in how many ways can you do it if you can put them weakly increasing in the rows and strictly increasing on the columns, right? There are 2 here, there are 4 here, and there is 0 here because you don't have enough numbers to fill strictly increasing, right? So then that tells me that this decomposition in this example is given by this. And as combinatorialists, right, we want to give an interpretation of this in terms of some combinatorial object, right? Then the question here is, how do we prove this, right? Like, how is this this proved? Like, it's a very beautiful theorem, right? And how, you know, how did it come about? And it comes from a very big hammer. Like, this is a very big theorem, right? It's a consequence of the classical Schur-Weil duality that tells you that here the vector space, right, is this tensor product, right? And you have an action of the general linear group, right? And that acts diagonally. And what does it mean to act diagonally? It means that it acts on each of the factors, like that, right? And you can think of this as being a matrix, right? And you're simply multiplying a matrix times a vector, a matrix times a vector, right? And this is, then you can write it as a linear combination. And like, so everything works out. So it's just linear algebra. And you also have this action, remember, the action of the symmetric group that permutes the factors, right? So, and the idea here is that these two actions commute. So if I first permute the factors and then I act diagonally, it's the same as if I first act diagonally by a matrix and then I permute the factors. So it doesn't matter. I get the same output, the same vector. Doesn't happen always, but in this case, it happens that you have two groups acting on the same space and the actions commute. So when this happens, you're able to define a representation of the direct product of the two groups. Like this group right here will act on this vector space, and you will be able to decompose it in terms of irreducibles, pairs of irreducibles. So these are just pairs. And the nice thing that happens in this case is that you have the same indexing set for the irreducibles. You see this lambda is the same partition on both, right? And there are going to be some restrictions. Here lambda, since this is have to be representations of Sk, they will be partitions of K, like, you know, diagrams with K boxes, right? And there is also going to be a condition that there are, you know, less than or equal to n rows in the diagrams. So it gives you a combined condition. So then out of this theorem right here, which is the classical Schur-Weil duality, you get the theorem that I showed you in the previous slide, because here I can think of making this the identity, right? And now I'm just going to have representations of GLN, or I can think here of putting the identity, right? And then I have representations of SK. So those groups are contained in here. And basically what this tells you is that if I want to decompose this in just as representation of the symmetric group, the coefficients here are going to be the dimensions of the representations in here, whatever this dimension it is. And if I want to decompose this as a GLN representation, then what I'm going to get as multiplicities here are going to be the dimensions of the representations of this. Like, it gives you this this duality, this very nice. And so how does it or result follow? Well, the representations of the general linear group, right, have bases that are in one-to-one correspondence with semi-standard tableaus. Right? And here, these ones, remember, are the tableaus that are standard, where you use all the numbers once, only once. Here you can allow repetitions, as you saw in the previous slide. So because of that, you get this, you get it as consequence. You can decompose it as a representation of either of the two groups. Yeah. So here is the pictorial correspondence that I want you to keep in mind, because this is what we have been trying to generalize with Mike, this picture right here. And like, so this is very classical. So here you have the ring of representations of the symmetric group, right? And basically all symmetric groups. So this is for all possible symmetric groups. And then as a ring, remember, a ring, you have to have a product. The sum is simply formal sum, right? Like you just kind of sum them like this direct product sum. But as as a ring, it has a basis, and the bases here are the irreducible representations for all possible essence, right? And the product is given by induction. So if you don't know what that means, it's just, you know, a way to construct representations for bigger groups, bigger symmetric groups from smaller ones, right? Like it's kind of a way to, so induction of representations. And here on this, right here, you have the polynomial representations of GLN. And this means that basically, when you represent these ones, like the entries are going to be like polynomials, the entries in the matrix, so you can find representations like that. So then in here, the product, the bases are these polynomial representations, and the product is the tensor product of two, like, you know, vector space tensor product, and then you have the action. And this right here is this Howe duality, this correspondence, right? That notice this creates a pairing. For every representation of the symmetric group, you have a representation of the general linear group. So it creates this matching that sometimes people call the Schur functor. But it's just Howe duality. And in here, right, you also have another ring that people study when they are studying representation theory. And this is the ring of symmetric functions. And here the corresponding bases are the Schur functions. And the product is just the regular product of symmetric functions, right, of power series. So then this is classical, right? It was studied by Frobenius, like this connection, the Frobenius characteristic, right? You can, every representation here corresponds to a Schur function. Every representation here corresponds to this. And then basically here, like these ones, right, the Schur functions turn out to be the characters of the representations. If you know representation theory, this turn out to be the characters of the irreducible representations here. So all of these ones are in correspondence. And when you multiply here, you take the tensor product of two irreducibles. When you induce here, or when you multiply this, the structure coefficients turn out to be the Littlewood-Richardson coefficients for all three products. Like the same, right? And in here, the combinatoric object that you're studying right here are these semi-standard tableaux, like tableaus that are weakly increasing, right? And so you have these that are filled with numbers, like you fill them with positive integers, yeah? So these are basically the combinatorial structures. And then there is this RSK correspondence, like that, the Robinson-Chenstedt-Knuth correspondence, that basically, remember what it does. You take a word, right? A word with letters 1 through n, and of length k, and you insert them, right? And then it gives you a pair, one being a standard tableau, right? Filled from 1 through k, and another a semi-standard tableau that is filled with numbers from 1 through n. So, but what this is doing, the RSK is creating a basis for this, like, you know, like it tells you how this one is how this is decomposed, because it's creating for every tensor word, right? Like every basis element, it creates a pair of objects, right? And those are precisely the elements right here, the basis elements in this decomposition. So it's allowing you to do this decomposition, RSK. So all these combinatorial objects help us understand the algebraic structures that we are studying, the representations, and it goes back and forth, right? Because here you prove this is a very big theorem in representation theory and allow us to see a lot of combinatorial results come for free. Does that make sense? So, okay, so then there is another action. Huh?
Can you back up? Can we have like a short discussion on that slide? Because I think you have such a great picture there. but I want it, the place where you say reps of symmetric groups, and you had said that this was symmetric groups for all n.
For all n.
But shouldn't it be for all k? That this is V tensor 1.
Yeah,
V tensor
so
2,
for all, yeah, so here in this place, right, the n is fixed. Yeah, it is fixed.
And
here,
so then
the k can vary.
Right, and so it's actually reps of symmetric groups of SK for all k.
For all k.
Just to clarify that
yes,
it's not.
Yes,
it's not
thank
SN.
you. Yeah, I meant n as a variable, but like, yeah, but it's SKs, all possible SKs. Yeah, very good. Okay, here n fixed. Here a k can be varies, right? Like for this k. Okay, very good. There is another action, right? Like the other action of the symmetric group, right? It acts on this this vector space. This is just like, n-dimensional vector space, and it acts by mapping the ith vector to the E sigma I. And as a representation, it decomposes like this. So you might recognize this as the permutation representation. So this is just so since this is a representation, it allows us to say that this is going to be a representation too. And the way that it would act is diagonally. You see, so you kind of act on each of the factors. So here is the example. That's why I did the other one before. When it permuted the factor, it would have left this one fixed, right? But now this one maps E1 tensor E1 to E2 tensor E2, right? It maps it to like, so this is a different action than the one that permutes the factors. Okay, so this is a different action. So this is now a different representation. And now notice here I have Sn, right? So then the question that one can ask is, how does this module with this new action, right, decompose as an Sn representation? Basically what I'm asking is there a combinatorial interpretation for these coefficients, right? Like how can I define them, right? I know that they should be, there is this lambda, right, which is like a tableau with boxes, right? It's going with n boxes in this case because it's an Sn representation, right? But then, what happens here, right? So here are some examples. And for these examples to make sense, I'm assuming that n is greater than or equal to 2k, right? Otherwise, some things will be not partitions, okay? So here, V1, we already did it, right, is this one. So here the two coefficients are 1. But when I do tensor 2, I get 2, 3, 1, 1, right? When I do 3, I get, so you see, so I want somehow to be able to combinatorially describe these ones, okay? So, well, what we notice is that this action that I just defined, I can think of it as, I can think of Sn, right, as a subgroup of GLN if I think of the elements in here as permutation matrices. If I think of these ones as being n by n matrices, I can think of this as just being the permutation matrices, okay? So we can interpret that the action that I had in the previous slide as a restriction of the action of GLN, right? Remember we had the diagonal action in the Schur-Weyl duality. So I can visualize that in fact I'm restricting the Schur-Weyl duality from having an action of GLN being diagonal to only having the action of Sn acting diagonally, right? So then here is the picture. I have GLN acting diagonally on V tensor K, and I also have SK acting by permuting the factors. And these were these actions, remember, commuting. So we think of these two as being commutants of each other, right? So then I restrict, right? And when I restrict, now this one is Sn. And then the question is, what goes here, right? Like, when I restrict, what will commute with this action, right? And so then you might wonder, why are you doing this? And well, because when I answered the question before, remember, like the dimensions, right? So whatever is in here, right, is going to be some algebra. And the irreducibles of this algebra, when I compute the dimensions, those will be the multiplicities that I'm looking for. So that's kind of like the logic here, right? That's why I want to find this object, find the irreducibles, and see, what the dimensions are to be able to describe the decomposition of V tensor K as an Essen representation. So then the question is, what linear transformations, right, commute with this action, right? So when you act, you get a set of linear transformations, right? And you're asking what transformations will commute. And like the transformations in this area of math, like, well, in algebraic combinatorics, we always want to have a picture for everything, right? You can visualize them as graphs. And like they are going to be graphs that go from tensor space to tensor space, right? You're going from V tensor K to V tensor K. So what happens if you enter a tensor product? So each dot right here is representing a tensor, yeah? Like, and then, for instance, this graph right here is encoding a linear transformation. And what it does, look, these are the Kronecker delta that tells me that it's going to be 0 if this index is not equal to this index, and it's going to be 1 if they are equal, right? So it's forcing this to be equal. So anything that has these two factors not equal will map to 0, right? So this is the condition here. And these two, since they are connected, they also have to be equal, right? And then when you map up, you see these ones are connected to this tree. So this tells me this tree have to be equal. You see E tensor A, E tensor A, right? Like all these ones are the same. And notice that this one is not connected at all. So then this can be anything. So you get the sum of everything. So connections tells you, so this is a way to encode like the linear transformation, right? So this picture right here. And one thing that people do here, right, is that this linear transformation right here can be encoded with a set partition. And the reason is because you can label the vertices here 1, 2, 3, 4, right? 1 prime, 2 prime, 3 prime, 4 prime, like that. And then what you would get here, right, is that everything that is connected, right, like this one, will go into a block, you see. So it's encoding by blocks, the pieces, right? And that's how you encode it. So for every, linear transformations will be encoded with set partitions. So the combinatorics. So it so happens that the object that goes in this box right here was discovered. So by Jones, the fact that they are commutants, and by Martin just as an algebra, like, so what Martin did is just define this algebra of set partitions, right? And define a product on the, that allowed you to do it. But Jones went the commutant version. Like he actually figured out what the commutant was, right? Like, he was actually interested in seeing what commutes with the action. So here you have so in order to define an algebra, like a finite dimensional algebra, you can give me a basis, right? Like of elements. And in this case, the basis elements turn out to be all possible set partitions. So this here is the notation for the numbers 1 through k. And these ones, the 1 prime up to k prime, right? Because I'm thinking of having two sets like that. Yeah. And then, so all possible set partitions. And notice that, remember in the previous slide, I had those graphs, right? But it doesn't matter how you connect them. The only thing that matters in this case is that they are connected, right? Like the same tree are connected. So the graphs do not matter, only connectivity. Yeah. So to be able to describe the transformation. And the product, right? So the product here is kind of very simple, but I kind of want you to, so what you do, if you give me two set partitions, I draw a picture of it, right? Like it doesn't matter how you draw it. And then you put one on top of the other. Like, you know, here is like the first one and here is the other one. And then what you do, you put them on top and then you identify. So this orange line here means that you're identified and they are becoming the same dot. Yeah. So you end up with a 3 layers dots. Okay. And then you look at this and you ask yourself, right, how many blocks in the middle? So you see the middle blocks are important, right? And this becomes, you see there are 2 pieces that are only in the middle, right? Like this graph has 2 floating middles right here. And you encode this as n squared. So n to the number of middle floatings. And then you just ignore everything that happens in the middle and you just connect what connects, you see these 2 up here, connect down, right, to this right here, right? And you can draw it in any way you want. These ones stay connected and then these are connected, right? But do not connect to anything on the top, right? And it becomes this. So that's how you define the product. So what I want you to remember from this picture is that there is a 3 layers, right? Because the idea is that you're putting one on top of the other. And there is this middle parts that you have to factor in, okay? So we will use the symbol pkn for this algebra, right? And here it is associative, right? And it has an identity. This is just the one where connects the, you know, the tops, right? Like that. And the dimension is the Bell number, the number of set partitions of a set with 2k elements. Okay, so that's kind of almost 2 more slides around and then the break. So Jones in 1994, like said that this was the case, that the partition algebra, right, when n is greater or equal to 2k is equal to, well, is isomorphic to, so this simply means the centralizer, you know, the things that like, you know, is a commutant, the commutant of the Essen action, the diagonal action on this space is equal to this algebra. So this algebra contains everything that commutes with the linear transformations that you get when Sn acts diagonally on this space, right? So remember, so here you have an action on this space diagonally. So then there is going to exist an action of this algebra. And I didn't write it because it's kind of, you know, it's not hard to define, but, you know, it's not important what it is. But this is going to also act on this vector space, yeah? So then you have 2 actions that they commute. So that means that you can define an action of this algebra, right? The same way as you did before. And if you decompose this as a representation, you get this, yeah? A decomposition like that. And here, lambda is going to be a partition of n, yeah? And you require that when you sum, starting at the second part up to the last part, this is always less than or equal to k, yeah? So the sum of these ones cannot exceed k. That's where the k condition comes in. And the n condition is that these partitions have to have n boxes. So now back to our question. Remember the question, how does this decompose as a representation of Sn, right? Well, the Howe duality tells us that this theorem right here of Jones, right, tells us that it's going to be the dimension of these representations, which are the irreducible representations of the partition algebra. And until, you know, I want to say until Mike and I started to work on this, people kept referring to this as the number of paths in some diagrams, like that are called Bratelli diagrams, right? And part of the work that we were doing with Mike, as a consequence, right, we obtained that actually you can give a descriptions in terms of tableaus, which, you know, is kind of starting to bring understanding of how all these things are working, right? So here, this d lambda is the number of set field tableau. Remember that when we were in the classical Shor-Bio duality, you were filling the tableau with single integers. Now you're allowing set field tableau. And the condition is that every number from 1 through k has to be used exactly once. So basically you have a set partition of 1 through k, right? And you fill the tableau with the set partition. And you're allowing empty boxes, right? Because here k, you know, k can be anything, but they can only occur in the first row. And they have to come before all the ones that are not empty, right? So here, notice, so this is the set partition, 1, 2, when 1 is by itself, 2 is by itself, and 3 is by itself. And you still have the weakly increasing condition. So here, the order that we use is that you look at the last element in the sets, and whichever has the smallest element is going to be the smaller element. Do you see this? 1, 2, 2 is smaller than 3. So this in the order, right? So here, 1, 2, is less than 3. So you fill them with all set partitions. So in this case, this dimension, right, is equal to 5 because there are 5 tableaux. Okay. So we were able to answer that question with tableaus, right? Like you kind of have like that. So here is like the picture, and then we can take the break. So remember, this was classical Shor-Bio duality, and here the combinatorics were semi-standard Young tableau filled with integers, right? Like that's important. They were only filled with integers in here. And I explained how this correspondence worked. So with Mike, we have been working on this restricted version, right? And basically, this part didn't exist. Like this part, we were able to identify with Mike. We defined these tildes that probably Mike has told you about, right? But we were able to understand this right here, right? Like this was done by John's work. It's not the Shor functor anymore, like, but it's Shor-Bio duality, right? This is the Jones defined this, right? So you have this correspondence right here. And with Mike, we identified what these functions were, right? But what we discovered, right, as you see that what I showed you in the previous slide was a corollary of what we were finding out is that the combinatorics in this picture right here were semi-standard Young tableau or column strict tableau that are filled with sets or multisets. All the objects that we kept encountering are either filled with sets or multisets. So then we started to look at, try to construct right here, the corresponding products, right, are all the Kronecker coefficients. If you induce representations of the partition algebras, you end up with Kronecker coefficients. If you tensor representations of the symmetric group, now this is fixed, this n is fixed, and this is the k that varies, remember? This turns out to be Kronecker coefficients. And if you multiply these functions that we defined with Mike, they turn out to be also Kronecker coefficients, or some, you know, n has to be sufficiently large for this, you know, you get what people call the stable Kronecker coefficients. So only the ones that are stable, but you get these Kronecker coefficients. So for instance, this correspondence is still not very clear what this correspondence is. And we started to try to think about, you know, RSK correspondence to try to understand, right, how the representations would help us find, you know, a way to understand these coefficients better, because you can use RSK correspondence to understand the Littlewood-Richardson coefficients. So we define we have defined an insertion algorithm, or many insertion algorithms, right? We still don't have the correct one, I feel, to be able to make further progress with that idea, right? But we were looking at different insertion algorithms. And as we were looking at different insertion algorithms, Mike asked me, you know, when you do the RSK correspondence, you have you know, you have the Howe duality, right? Like you have kind of like, you know, you could insert, you can have generalized permutations where you can both tableaus turn out to be a, you know, a semi-standard, right? And this is the Howe duality, right? So he was saying, and then he asked, is there some algebraic, something that has, you know, that acts on polynomial rings? And that's the second part of the talk. I want to tell you like how we were able to answer that question, like, you know, in terms to try, but the motivation came from this RSK type correspondence that we were looking at. We were looking for the motivation to try to understand, you know, what algebraic objects correspond to the combinatorics that we were observing. So here, remember the vector space here is V tensor K for both, okay? So what if, so then the idea here is, what if we change the vector space, right? So a GLN acts on the polynomial ring, and you can look at this action in the book by Goodman and Wallach. So perhaps the best way to understand this one is your vector space now becomes the n by k matrices. And so you could think of them like this, right? Like, and you could think of the entries in the matrix as some variables. So then if you give me like a matrix in GLN, I can multiply on the left, right? And get some different looking entries, right? So I can think of the entries as functions on the vector space when I act with my GLN. So so I can think of the polynomial ring as the space of polynomials in these variables, yeah, where I goes from 1 through n and j goes from 1 through k. And since GLN acts by left multiplication on the matrices, this induces a representation of GLN on the polynomial ring. And the way is that if you give me like a matrix in GLN and you give me a polynomial, like the action, so this is rho is for the action, on the polynomial is simply by f, and then you multiply times the inverse of the matrix, this matrix right here. And whatever you get there, right, this becomes some new variables in the polynomial, okay? So then the question is, what commutes with this action, right? So you have an action of GLN that acts on the polynomial ring, right? So this is my new vector space, and I want to know what commutes. And what commutes is actually pretty simple, and the proof is kind of like, you know, associativity, right? So if GLK, right? Because these are n by k matrices. So, you know, I act on the left with an n by n matrix, and I can act on the right by a k by k matrix. Yeah. And since associativity, right, since matrix multiplication is associative, then you have that the actions commute, right? It's kind of pretty easy to see in this case. So then you have an action of GLN and an action of GLK acting on the same vector space. The actions commute. That means that you can define this right here, like the an action of this group. And so I want to remind you that the vector space breaks into homogeneous pieces, right? So these are all the polynomials of degree R, right? In whatever these variables are. And the dimensions are given by multisets. Look here, right? Where R is the degree, right, of the polynomials right here. So there is a theorem in chapter 5 of the book of Goodman and Wallach that tells you that this vector space will decompose as like the same way, you know, and this we are calling Howe duality. But in the book by Goodman and Wallach, they only call it Howe duality when you are restricting to the action of the symplectic group. Like that's what they call Howe duality, which happens to be a subgroup of GL2N, right? And what they find is that the commutant is the Lie algebra, like the special orthogonal algebra 2K, right? So this is what they call Howe duality in this book, but it's the same action, just restricted, right? So we just call Howe duality the whole thing, but you could also think of this as Sherville duality, if you like, since you're simply computing commutants, right? And the idea here, right, because you have this theorem, this decomposition right here, if I want to just look at this as a GLN representation, I can ask, you know, what are the multiplicities of the irreducibles, right? In the same way as I did before, right? What are these multiplicities when I decompose this simply as a GLN representation, just a homogeneous component? They happen to be like, you know, the action on the homogeneous pieces, right? And I want to know what these coefficients are. And they turn out to be, in this case, right, is the number of semi-standard tableau or column strict tableau of shape lambda, where lambda is a partition, with less than or equal to n rows, right, like the partition lambda. And you can choose only numbers from 1 through k. You see, it depends on that. So that's what this number, these multiplicities are. So using Howe duality, you can decompose the polynomial ring, okay? Into like, and you could also be able to decompose the GLK, and the only difference is that the n and k will switch here. Okay, so then there is, so Sn also acts on the polynomial ring, right? So here the symmetric group is contained in GLN, right, as permutation matrices, as we saw before. And now you know, so if you give me like a monomial, right, any monomial in the polynomial ring of degree R, right, on the homogeneous component, then the symmetric group acts on the first index. So these ones have two index, notice, like some i's and some j's, because these were the entries in the matrix. Remember, if you think of them like that, or just as variables. So then it will act only on the first entry. And we put inverse because, remember, we are restricting the action of the general linear group, and the action had the inverse, right? Like when you did the action. So this is just a restriction. So it acts. So then you can ask again, right? How does the polynomial ring decomposes as an Sn representation? And actually, this was the question that Mike asked, you know, when we first started to look at this, right? We wanted to understand this, these coefficients right here, right? When you decompose the homogeneous polynomial, the space of homogeneous polynomials, right, of degree R, as an Sn representation where the action is given by this right here, right? And so basically, you know, if we follow the recipe that I have been giving you, the problem would now be to find the commutant, right? What linear transformations commute, right? So we know that GLN acts on the polynomial ring. We know GLK acts on the polynomial ring, and this is called Howe duality. So I can restrict this, right? It's the same action, right? And I want to know what goes into this box right here, because whatever goes inside of this box, right, like the irreducible representations of what goes in here, the dimensions are going to be this multiplicity. So if I want to answer this question, I want to find what goes in here and compute the irreducibles and find their dimensions, okay? So, and what we found is a new algebra, like remember the partition algebra, but now this one is not a partition, is a partition still, but of multisets. In before we have partitions of sets, now we will have partitions of multisets. And so I try to do with colors so that kind of it looks pretty. So remember that a multiset is simply like a set that allows repetitions, right? So you're allowing repetitions, and a multiset partition is a multiset of multisets. So you just like a set partition is a set of sets, right? A multiset partition will be a multiset of multisets. So here now you can also have equal pieces, right? Equal parts. Like when you had the set partitions, that didn't happen because everything has to either occur or not occur, right? Now this one you have multiplicities, right? So, you know, so and the set partitions that we will be interested in, I'm going to use this notation gamma r sub k, r, remember the degree of the polynomials, and I will have a variable k here that will be the indexing for the for this algebra. And these set partitions, these multiset partitions will contain 2R elements in total. And they will also, and their R will come from a set 1 through K, and another R are going to come from a set 1 prime to K prime in the same way as before, right? Like as we had before in the previous picture, except that now you could pick the same element always, right? You could pick R1s or an R1 primes, right? So here is an example, right? So here is a set partition that will be contained in this set when K equal to 4 and R equal to 5. So I can create any set partition as long as the number of non-primes is equal to 4, 1, 2, 3, right? 4, yeah. And then the number of primes is 4. Is 5, sorry, they have to be 5. 1, 2, 3, right? 4, 5. And then the primes are also 5, right? And then all the numbers that are in here are between 1 and 4, right? So that's the only conditions. And so this is it, but you can visualize this in pictures, right? And notice that I color coded all the 1s and 1 primes blue, all the 2s, right, orange, and all the 4s, even if they are primes or non-prime, pink. So this is what's going on, okay? And you can have these pictures now. And just so that you see how it works, right? Like now I can have the same label. So this is the special case when K equal to 1, okay? And R equal to 2, right? And here N can be anything greater or equal to 4. And in this case, there are 9. That's the total, right? And these are all the possibilities, right? And so you get all these diagrams right here. And this is what's going to be my basis, right? It's going to be the set of diagrams or or multi-set partitions that I showed you. Yeah. So anyways, and the idea now was that we wanted to define a product, and I try to color code everything so that it's not so hard to understand, right? So remember that when we multiply like the set partitions, we were putting one on top of the other one, right? So here, this set right here is all triplets. Like you have 3 levels, right? Where you're going to have some not prime once and prime 2 times, right? 3 level diagrams. That's what this says. Then, you know, for every 3 level diagram, there is going to be some data that you're going to accumulate. So remember, something that was important were the middle pieces, right? So these are the middle blocks, the beta, right? So it just keeps track of all the middle blocks, yeah? And then the other parts are keeping track of only what happens that goes from the top to the bottom, right? Like, so it keeps track of this. So this is this part right here, that these restrictions simply are telling you only, you know, the notation seems kind of, but simply what's going on, right? Like you're kind of dividing it into the stuff that is only in the middle and the stuff that goes from the top all the way to the bottom, because that's how you did the product before. And this is what this is doing, right? And then in this case, before, remember, you had some coefficients which were powers, right? Now you're going to have some coefficients too. Sometimes they are going to be just numbers, and they will simply depend on the data related to these blocks, right? And some will depend also on this, on a variable x as before, right? And this is going to be some falling factorial, like, you start with x and you fall however many middle blocks you have. Remember that this, when you were doing the partition algebra, it depended on how many blocks you had. So this also depends on the middle blocks, right? And these are just numbers. So look, here is an example. Like you have this triple decker right here, is contained here. And notice this contains 9 not prime numbers, 9 prime numbers, and 9 that are prime twice. And I'm only having numbers 1 and 2s, okay? So these ones right here, the ones that have only primes, these are the middle blocks, yeah? This is kind of what it stays here in the middle. And then these restrictions, you ignore anything that has only primes. You ignore them, right? These are kind of on the way to the bottom, right? So you ignore the primes and you just write things that have only not primes on double primes, right? And you get this. So this is what this restriction is, right? Top, bottom, ignore the middle, okay? So then you see this data right here, how many blocks does this restriction has? You just count, and you have 10, 1, 2, just count them, right? 10. And there are 6 that are different. The pink ones, these green ones, right? There are 6 different ones. Those are my possible S's that will allow me to compute this. And for instance, if this is the S right here, yeah, S equal to just this set partition that contains only 1, yeah. Then I look at this new S right here, right? And these are just, the blocks in here, right? That contain this element, yeah, 4. Then I store the data, how many pieces does it have, and how many pieces repeat. Notice there is only 1 of these, 1 of these, and 2 of these, yeah? So I record 1, 1, and 2. Right? So this is recording the multiplicities and the length. So I can compute 1 factor in here, and I have to do it here for all 6 to obtain this number. And then here, right, this one, here I have 3 middle blocks. So there is going to be 3, right? You start x minus 10, right? X minus 11 and x minus 12. That's the following factorial. And then these multiplicities here, right? I computed how many of the same kind, 2, and 1 different, 2 factorial, 1 factorial. So this is what these numbers are. So then this allowed us to compute this. Notice the product of those 2 are the coefficients that you get when you define the product in here. So the multi-set partition algebra, right? You get all possible set partitions, multi-set partitions, and this is the product, and you just multiply those. So computing like the hard part here is looking at all the possibilities that you can have. Notice here you have all the triple deckers that you can get, and the conditions are that, this, if you only restrict yourself to the top, it looks like pi. If you only restrict here to the bottom, it looks like the gamma, right? And then you have to look at all the possibilities that you can construct. So here you have this one. For instance, if you multiply this times itself, right? These are the, ignore the middle parts, right? And you get these diagrams. Then you do the computations for each of them, right? Like these products, and these are the coefficients. So then that gives me a way to multiply this, okay? And I did another example, so you see that it works for bigger numbers, not just when it's 1 and so this is for, it works for 1 and 2s, right? So in color coded, the blue ones are the 2s and the pink ones. And one thing that that you should notice here is that in order for me to be able to multiply these two, this here has to be equal to this. Otherwise you get 0. Right? Like it has to match up the color coding, right? And but you can actually do the product. So over time, so maybe I just tell you that this, in fact, we actually showed with Mike that this actually corresponds to the centralizer, right? So I'm going to just, you know, that you can match it to what people call in, you know, when you're studying centralizers, there are orbits when you have a symmetric group action, right? So this turn out for every orbit in the group action, you will have an element and we were able to match it, right, combinatorially. And we were able to answer the question. So basically, you know, by showing that these were commutants with each other, we were able to find these coefficients. Remember, we wanted to decompose the polynomial ring as Essen representations. And what we found is that they are going to be multiset field tableau. Like in a very nice way, the multiplicities are described by multiset tableau, right, of some shape like lambda, right, that contains R values are chosen from this set. So basically, you know, you could choose all ones, but you have to choose R of them, right? So all possible ways to fill them up. This is what these numbers are. So you again have tableaus filled with multisets now. Remember, for the partition algebra, they were filled with set partitions. Now they are filled with multiset partitions. And for the classical case, they were just filled with numbers, right? So I just want to say that there has been some recent progress on this, right? My student Alex, he has shown that there is an isomorphism. This here is the partition algebra, and that you can construct this algebra using this homomorphism. So then, like, the reason that this is kind of nice is because we can try to extract information about the partition algebra to be able to find, you know, better ways to do things. So for instance, to find a simpler product, right? Like the hard part when we were doing the product was figuring it out all possible triple deckers. But now this one, right? This is a new basis. So it's not the same basis. In this basis, all you have to do is do permutations of the blue dots and the orange dots in the middle right here. This is where this is coming. Look, 3 blue dots, 2 blue dots. And then this 2 is coming from the fact that these 2 are connected. You get repetitions. And then you get all possibilities of being able to permute these 2 to get like a sum. So you get this, and you also get generators. Like he has been able to find a set of generators using this, and hopefully one day relations. And trying to understand also, you know, do a combinatorial construction of the representations. Okay, so thank you.
Awesome.
Yay.
Let's thank the speaker. Are there any questions? Just a warning, it's 7 minutes after 4, so if you have to go for a meeting or something, then you should probably head off. But if not, any questions, just unmute and go for it.
So in your last, the multiplication that you have initially is so complicated that It must be very, very difficult to compute because you never know if you miss some.
I know.
You have it programmed or something?
Mike has it programmed. Yes. Mike programs everything. He's amazing.
And when it's not him, it's somebody else in our group.
Yeah, so it's programmed. It's programmed.
Yes, but the essence is, I like the fact that your student tried to find a new basis, essentially using some symmetry, and then the multiplication seems to be much simpler using a different basis.
All that is going on is that you're permuting these ones, right? And permuting these ones. Because
so have you explored other bases?
You know, this is one of my big questions, Nantel. Like one of the big things is independent even of this. If I take this if you take the orbit basis in the partition algebra, it's not a monoid in that sense, yes. Right? So one of my questions is it possible, does there exist a basis, right? Such that it's kind of monoid-like? That, you know, you multiply and you obtain one. And at this point, my suspicion is no, but then it still remains the question, is there a monoid, right, of multi-set partitions, right? Like, you know, in the same sense that there is a monoid of set partitions.
Yeah, with the polynomial coefficient or
right.
Or
yeah,
it
doesn't,
simple.
Yeah. It's just a single, right? In this one, you know, using this, you know, this is just a projection, right? So basically, we are projecting partition algebras, right? Using this projection, because this is, you know, a subgroup, right?
I understand. So this is kind of taking, that's why you just need, when you do the product, you just need to concentrate on the permuting the middle, because the permuting the top and the bottom is already taken care of through the projection.
Right.
And yes. Have you tried to for small n and k to program it and try to see if there is a change of basis that makes it monoid-like?
I tried for, and you know, but yeah, I come very close, but there is one that has to, or like, you know, kind of like, so I've you know, I have constructed some, but I cannot find it. So then I have asked Alex to try to prove that, you know, it's not possible to do this for 3, right? Like, or for 2 even, like, you know, that you will not be able to find like a basis in that case, right? So if he can prove that, then, you know, perhaps there is a monoid structure, but it's not related to the centralizer.
Okay.
Rosa, why are you not stating that the insertion that we did is the right insertion?
Oh, for this. Oh, no. I was saying for the Kronecker, right? It doesn't, when I said that it didn't help us understand the Kronecker, but for the insertion that we did works for this, right? And it works for diagram algebras. But does it help us understand Kronecker? No, right?
Well, I don't know. It's like to RSK understanding Littlewood-Richardson means you also have to have this additional structure.
What additional?
Of lattice.
Of lattice.
You right, you have to know where the lattice, or what is highest weight, what is this kind of crystal structure behind it. So I don't know if that's, I would say that that's in addition to RSK.
Okay.
And that's the element we're still missing.
Okay.
But who knows, maybe that's just not even possible.
Yeah. So when I said it didn't help, I mean, it's because I haven't found a way to make it And I remember every time that I worked, it didn't actually, we were not able to find a way to define lattice, right? That was always a problem.
I agree that there's that there is this insertion that we've come up with, and it doesn't seem to be compatible with RSK, and that you can't say if I match up RSK to what the other one is, then you don't get how one decomposes in terms of the other.
Right.
And I feel like I've got enough examples to say that that's probably not even possible with any insertion, or with any insertion that's similar.
Yeah, I guess that's what I had in mind when I was saying, like, you know, because we, for a while, we worked a lot, right, on this, trying to make it compatible, right? And we couldn't make it compatible with all the insertions that exist. I feel like we tried. So,
and I think we're not the only ones who've tried as well.
Yeah, a lot of people have tried, but perhaps you're right. Perhaps the right approach would be to just ignore this compatibility and just concentrate on trying to find the condition that will make it work, right?
Are there other questions, or did you want to say something, Mike? Sorry, I just saw your mic.
I could ask one more question, but if there's other people there.
I think so far no one else has unmuted, so you can go for it while other people.
Okay.
I'm not muted.
Rosa, on your slide that you had at the break, you had question marks next to the Frobenius map.
I know it's not so much of a question mark because you sent me that. No, this
well,
one.
No, you're right. It is question mark, and that I don't think all that we could do is established. But I do actually think that the Frobenius characteristic is exactly what you would think it would be. It's that a partition algebra element is the Frobenius characteristic of a partition algebra element maps to this
remember
character
that
basis.
That observation that you made about the restriction and having these representations of the partition algebra, and like in those representations that we were defining, I think that's the correspondence. Like when you were talking about the restriction problem in the setup of the partition algebra, and remember how we were defining these representations, right? Like using these set partitions, right? And I was kind of thinking that was the correspondence with that setup, but yeah, but it's still a fog.
Yeah, I say there. You're right to put in question marks, and that we haven't really filled in all of the details. But if you kind of define the Frobenius character map is to map irreducibles of the partition algebra to the symmetric function basis, then induction does go to the outer product, and restriction does go to the coproduct. But have we proven everything? No.
Nope. You're skiing, Mantel. You're even moving like you're skiing.
Are there other questions?
Yeah, I have a question.
Go, Anna.
Hi, Anne.
Hi. So at some point you used a particular action of the symmetric group, right? The one. So what happens if you use a different action of the symmetric group? Then you would have to like do the whole program again?
Yeah, because the commutant depends on the action, because when you act, you get a set of linear transformations, right? Choose a basis, right? Of the vector space, act on it, and you get some matrices. Now you ask what commutes with those matrices.
Yeah, so for example, there's a commuter in crystal theory. So and that actually gives a symmetric group action. So I'm wondering, has
if
anybody looked at that?
yeah,
Like what you would get in that case?
right, because that's how this project started. Mike asked, you know, what do you get, right, when you do this? And people didn't know, and we were surprised that people didn't know.
Okay. Well, I'll ask you some more questions later.
Yeah, that would be great. Yeah, because because this is actually a machine, right? Like you
Mhm.
kind of actually, you know, every time that you have an action of GLN, you can kind of restrict it, right? Or you could kind
Mhm.
of, you know, to get this kind of algebras and understand how they fit together.
Right. I'm just wondering whether there would be better actions to study.
Right.
Anyway, I'll
Yeah,
ask
yeah,
you
yeah.
later.
Okay, sounds great.
Any other questions? All right, seeing none, let's thank the speaker a second time.